All right, so in this lesson, let's formally learn about functions. Okay, so we are going to learn what a function is, okay, how to operate with that, and what it does for us, and many other details will come out throughout the lesson here. Okay, and so before we get started, I highly recommend that the following skills are required prior to learning about functions here. So you need to know what a variable is. You need to know what an algebraic expression is, okay, and you need to know what an equation is, and certainly you need to know how to substitute a value, a numerical value, into a variable of a given mathematical expression, okay. And so those are the only requirements, the only sort of like the prerequisites before we head into this formal lesson here. All right. So let's say you have a given expression, and that's why I said earlier, the prerequisite for this lesson is simply you just need to know what an algebraic expression is all about. So now you given an expression as following: it's a 3x minus 1. It's an expression. The reason we call it an expression now, well, hopefully I don't have to go too far back into the even further elementary algebra, but an expression, it just tells us, what this will do. Okay, so or it indicates that any reader who reads the problem here, say according to this expression, it says whatever the variable is. So once you know what the variable is, once you know a value of the variable, this expression tells us that we just simply multiply the value being represented by this variable with 3. So 3 multiplied with the quantity represented by the variable and subtract 1. So for now, it's simply a mathematical expression. It's an algebraic expression. Okay, 3 times the quantity represented by the variable x here, minus 1. Okay, so what you have here is an expression. And I didn't say anything about function or whatsoever. Don't worry about that. Okay, all I need you to understand is this is an expression, just like any of those expressions you have already learned prior to studying in this video lesson. Okay, so it's an expression. And so now, yes, just like that, let's make a quick note. So x is the variable, and you will also have tried this. Have already knew about that, well aware about that. X is the variable. So now how about compute or evaluate or find the final value. Okay, if x equals 1. If x equals 1. So the idea now is that this expression is only a general expression that says, hey, anytime you know the value for x, you're just going to multiply x with 3 and minus 1. Anytime you know a value for x, then generally you just, according to this expression, then it generally tells you that for any value of x, you're going to just multiply x with 3 and minus 1. But now, since in this problem we step a little further, we're not generally looking at the expression anymore, but now we want to specifically come up with a final numerical answer when x equals 1. Okay, so when x specifically equals 1, what does this expression say? This expression says in order to calculate, to compute, to calculate, I also forgot, I should have also mentioned that term, calculate. We can calculate, we can say we can compute, or we can say evaluate. Basically we want to come up with a final numerical answer. Okay, so when x equals 1 specifically, okay, so this expression tells us, indicates for us that we multiply 3 with the quantity, now no longer represented as an x, but specifically 1. So 3 times 1 minus 1. Okay, and by the way, needless to say, you need to know how to do basic order of operation. Okay, so multiplication comes first, so 3 times 1 and minus 1, we're looking at 2. Okay, so we have a given expression. We're giving our variable a value. Okay, and this for now, the variable is just simply a variable being part of it, the expression right there. We're giving our variable, we're giving in. Okay, we're giving our variable a value, and then this now all of a sudden we realize that the 3 times 1 minus 1, the 3 times the value minus 1 gives us here an output. Okay, it's an output here, but in the end, this 3 times 1 minus 1 is a rule. Just now we recognize that it's a rule. We can treat that just as a rule, just fine. Okay, so now to clarify, x equals 1 that we're giving it, that we're providing it. Yes, it's an input. It's an input. Okay, see, so right here it's an input. And this expression itself, all of a sudden we realize it has a different meaning. It has a different impact for us. We can use that as a rule. To emphasize what I'm saying, that the 3x minus 1 is a rule. Okay, we can choose x equals 0. Okay, now it's a different value assigned to x, but this rule stays the same. 3 times 0 minus 1, and that's why I can say that it's a rule, because regardless of what value we're giving it, it has to follow this. It has to follow this specific expression. Now we call that it's a rule. Okay, so 3 times 1 giving us, that's making it the 0 minus 1. The final outcome, the final output there is a negative 1. The final value is a negative 1. So again, what I see here, that's the rule. Having a little bit struggle with writing in a narrow space right here, but it's a rule. The three times the input right here, the 3 times the variable value minus 1, that's the rule. Now all of a sudden we realize, because we can apply that exact same thing on other values, and then this specific part right here is the input. Okay, because we are providing it, because it will be substituting in for the expression, and then this final outcome right here, the rule determines this. The rule determines this final outcome. So this is now, we can now call that as the output. Okay, so same expression right here, but you come up with different values right here, depending on your beginning input right here. But in the end, there's a rule. There's a rule, and we have our right to give an input. Okay, and here the input, here specifically in this mathematical expression, the input is just a value, an actual numerical value for our variable. Okay, and then the expression itself is a rule. And sometimes an expression here has another name. It's a formula. An expression can also be a formula. Okay, so according to this formula, according to this expression, now we see that as a rule. Okay, it takes this input. What does it do to the input? This rule tells us to multiply the 0 with 3. The inputs here we multiply with 3 and minus 1. That's the rule. And in this case right here, we clearly see how the rule is ran. The rule is ran by just 0, the inputs times 3 minus 1, and that's that. After that process, we come out with the negative 1 as the final output. Okay. All right, so there's a rule, there's an input, and there's an output, and just like how it was, and this is here a lot more friendly to those who are concurrently studying math, who are specifically in math. And this problem is the closest example. It lives right in our daily lives, at least for the length of an academic term like that. Okay, so an expression now, a mathematical expression with a variable, is now a rule, where you can give different values for your variable. Okay, so x here in this case is the variable, and the whole idea of variable is we can take different values. And so you know all of that idea prior to learning in this lesson, and so you can switch to different values. So according to this rule, right? So the different values that we switch to on our variable right here, we can call that, we regard to those as the input. So the variable x here is the input. Okay, we're giving it into the rule here, and this rule says that we're going to multiply the input value with 3, specifically for this rule. Multiply the input value with 3 and minus 1. Okay, and that's what the rule says, and the rules, according to that rules, and we determine that the final value here has to be a negative 1. So that final value comes out from this rule, so that's why we call it, it's an output. Okay, it's an output value. Okay, it's an output value. All right, so I've mentioned it, but now let's formally write it down. So what's common? Okay, and of course, I mean, what's common here is what's common among the three examples that I brought up. All right, so the number one thing, most important one, is a rule. Any one of those I brought up, it's a rule. Okay, it's a rule that's relating. Hey, we're taking one value, inputting, and then we determine that. So in the end, input and outputs, they are relating. They are related. That's why I'm using this term. It's a rule that's relating the two variables. Okay, there was a rule relating the two variables, the inputting variable and the outputting variable. Okay, the input variable and the output variable. And yes, see, there's an input variable, the one that we're giving in. Okay, it's called the input variable. It's given in. Okay, and then I leave a little space because I want to come back here and make some further notes on that. And then the rule process the inputs, as you already saw how that worked. The rule process the inputs to determine the output. So we come out with an output, and the output itself is a variable. Okay. See, this output variable or this output value is determined by the rule. So the rule, to me, is the most important thing. There's a rule, and then it takes an input and to determine, to calculate the output. Okay, so determine is a more the general wording of that, but calculate, in case it's a numerical value, then we can calculate and get an output. All right, so, but here's the thing. Just having these three elements is not enough to make what's so-called a function. Okay, it's not enough to make what's so-called a function. Each input, okay, one and only one output. All right, each input, so any of the problems I've done earlier, and including the expression 3x minus 1 that I brought up before I erased it, you see, you're giving one input, x equals 1. 3 times 1 minus 1 equals 2. Okay, the calculations say so. If the next day for different students is x equals 1 again as the input, but 3 times 1 minus 1 equals 5, something's not right. Okay, something's not right. So in the way it is, it needs to be only one output. So if it has multiple outputs, it's a completely different story. So what we want to focus to is each input determines only one and only one output. Okay, no exception. No exception. All right, so now in that way, so I wrote these three down earlier, but that's not all the things that need to be that are common between the three examples. There's one more that I just now brought it out. Okay, so each input, okay, each input, okay, determines just exactly one and only one. I'm making it extra strong about that statement. Exactly one and only one outputs. Okay. Each input through the rule determines exactly one and only one output. Okay. All right. So now, indeed, at the end here, we actually have 4 fundamental characteristics. The number one thing, the most primary thing, the most primary characteristic it's a rule that's relating two variables. But they're not only a rules. Now, so the two variables are the input variable and the output variables. That's easy to know and quite directly relating to this. What I said earlier, it's a rule relating two variables. But then that rule is not just relating. It's not just relating. It has to relate in a way that each input, okay, each input determines exactly one and only one output. That's what matters right there. That's how important it is to have. All right, so at this point now we are ready for a formal definition of what a function is. All right, a function is a rule that determines exactly one output. See, so it's a rule, it takes input and it gives output. So that's why back on the list that I listed down, the common, what's common between, among the three examples, and yes, there's a rule. Okay, so the first thing to nail down anytime we hear the term function, hey, we have a function to work with. Okay, so this is the function and that is a function. Think of a rule. It's a rule. And that rule will be relating to variables here. One of them we call inputs, the other one we call outputs. That's what it says. A function is a rule. It is a rule. A function is a rule that determines the way that it takes the inputs and it determines the outputs. But it determines, here's the requirement. So the bottom one that I wrote on my other list, exactly one output for each given input. Okay, so that's in one statement, in one sentence. That's how we define what a function is. Okay, so now from now on, and there are many professors out there who would like to explain, and you have to understand, many professors explain the idea about a function differently, but any of them, including me, has we have our own way of interpreting what a function is, but any of them and all of us, eventually we all come to the same understanding. Okay, so I would like to emphasize for my students, whoever learn with me, that a function is a rule. I want my students to see a function is a rule. Okay, that's the most important thing to emphasize. And then that rule has a requirement. It has to determine exactly one output for each given input. For each given input. Okay, let's look at function notation right here. Okay, so it could be a title of a discussion on its own, but I would like to just put this as a subtopic, in our main general understanding of what a function is. Okay, so it's part of our current going on video lecture here. So now we're looking at function notation. And I'm going to show you a couple of different varieties. Okay, so function notations, different ways of how we notate a function, how we can, on written form, okay, on written paper. Okay, so 3 times x minus 1, and we investigated this clearly. This rule says anywhere we have an input value, right? Once we give an input value for x, once we substitute a value, a numerical value for x, then this rule says we multiply the input value with 3, and then minus 1. And I do my work here to follow strictly with the order of operations. And so there's a rule. Okay. And now we have investigated further that one input gave out only one output. So now clearly speaking, this is this rule clearly is a function, because this rule meets all of the requirements to be a function. It's a rule relating between an input, and any inputs assigned, we come out with an output. And then any one input only gives exactly and only one output. So this rule here is a function, clearly. Okay, but now we don't want to always write this down. Hey, 3x minus 1 is a function. It's a rule and it's a function. We don't want to always write this down like that. And that's the whole purpose of coming up with a function notation. Okay, and so now let's roll back to that point where we understood already that this is a rule. The rule says from this input, right, we're gonna multiply that input with 3 and subtract 1. So with this rule right here, I'm gonna name the whole rule. All right, I'm gonna name the whole rule here as I'm going to give a letter. And the letter choice here, yes, very traditionally, the people, authors throughout many textbooks use a letter F, a lowercase letter F, maybe because that's starting out for function. But it's just a name. So this whole expression here can now, in short, be represented by a name F. And this is a function. So the function here has a name, F. And now, in this notation, after indicating the name of the function, now I'm going to use a pair of parentheses. And I'm indicating with the x. So now this x has to be matching with that x in our rule over here. So that's the whole notation of our function. So this 3x minus 1 is a function. We name that x. And it's a function where it's indicating, so this parentheses, with this pair of parentheses with the x indicated here, it's an indication that in this expression, the x that appears in our expression, in our function, that is the input. Okay, so now with this notation, let me break it down even more in detail here. Okay, so just the f itself. Okay, just the f itself. This is our functions. It's the name of the function, or for short, it's the function's name. Okay, it's the function's name, just that letter, and then the x being, and so it's always, if you just write fx right here, right like this, it's not enough. You have to indicate the x with a pair of parentheses around. Okay, so, and this is the proper notation for that. So the x that appears inside of the parentheses, of the pair of parentheses, it's an indicator. Okay, this an indicator. It indicates. Okay, it indicates that the variable x in the given rule. Okay, in the given rule, this rule initially came out as an expression. Okay, and so it now indicates the rule here, the x in the given rule is the input. Okay. All right. Once we come up with a notation, then we have to learn. We need to get use of how we say it out. Okay. At least in English term. In English term, then this symbol, this notation, the way we say it, the way we read it out loud, f of x. Okay, that's the way we read it. That's the way we read out loud. That's the way we pronounce it. Okay, this notation, we read f of x, but it means it's a function with the name f. And then, so f now legally represents that rule. Okay, and then to be specific, and very important to be this specific right here, that this function takes the x as the input variable. And so in that way, it makes sense perfectly, it makes sense logically that upon giving it a notation, then the whole idea now together, we have already agreed that this is a function, and we learned about the function notation. So now it logically it makes sense that we write f of x, and f of x logically equals 3x minus 1. Okay, so there you go. This is the function name. Once again, that's the logic of that function's name. This indicates when you're looking at this expression, look for that x. That's your input. Because another way of saying, another way to explain why indicating the x input variable here to be important is that once you see this, then when it gets to the step where you substitute value in, and you will know which variable to substitute value for. And then this is the rule. Okay, and so welcome aboard. This is a formal function notation. You write function name in parentheses that indicates the variable's name, and then it equals to the actual rule, where the rule is. Why is this convenient? So now it's not a formal example yet to be brought in this current lecture, but I will bring in some formal example. But for now, let's quickly see how convenient that is. So once you call this rule right here as a function f of x, f of x, that's how I say it, but as a notation, f in parentheses x. Once we give it a name, then let's look at the impact of coming up with a symbol. Coming up with that notation, here's the impact. So now, see? So now when you're looking at f of 1, for example, this is how we read it. F of 1. No longer x, f of 1. But see, this is the convenience of using a notation right here. That means, this means x equals 1. We substitute 1 in place of x. We substitute 1 in place of x. And so it means now, see, x here, and compare with the original symbol, compared to the original notation f of x, then this is, instead of being x, it's 1 here. So that means in our expression, 3 times the input, 1 minus 1. Okay, and so now according to the rule says we multiply 3 with the input. So 3 times 1 minus 1. Our output here is 2. Okay. All right, so in that way, so now we are starting to get a little better, getting a little through, okay, with the function notation, and see how convenient that is. And so now allow me to, I'm still leaving this particular one on the board. So what about f, okay, of 4, and you can see it, I'm saying it out loud in front of the camera right now. F of 4, see, saying it, f of 4. But so wait a minute, compare with the f of x. Compare with the f of x, what's the change here? We substitute, see, we substitute instead of x, we substitute 4 for that. Okay, so now the rule says, see, in your rule it's 3x minus 1, 3 inputs minus 1, 3 times the inputs minus 1. But so now instead of the inputs, now I'm going to look for that input and then substitute that with 4. And that's why that's why I use parentheses here, and I highly recommend any of my students to use a parentheses anytime you throw in a substitution, a value substituted for a variable. Okay, so 3 times the inputs substituted by 4, formally x, generally x, but now 3 times 4 minus 1. Okay, and so now we come up with now this final value right here. So 3 times 4 is 12 minus 1, that's 11. Okay. And so now I need to make further notation. This is inputs, as you already knew. This is inputs. Okay, as you already knew. But so now this one here is called outputs. Okay, and this is output. It's an output, indicating it's something that came out from going through this rule or being determined by that rule. Okay, but the final value is not always the same. It's different values, and just like that, each one input gives you exactly one output. Okay, let's try another one. So now instead of f of x, I can put in f of negative 1. Okay. All right. We substituted the inputs. We substituted the variable primarily decided as the input for negative 1. So negative 1 substituting for x. So now in my expression 3, but instead of x, I write negative 1. So 3 times negative 1 minus 1. And now it gives me, so 3 times negative 1, order of operations, and then gives me a negative 3 and minus 1, so it's a minus 4. So this is our output. Okay, this is again in inputs. Okay, and to step even another wild step for here, I want anyone to have a broader understanding of how important that is to have that symbol. So now, but what about f of h? Okay, we don't always have to substitute a numerical value into your variable. You can substitute another letter into your variable. Substitute another variable into your current input variable. So now what does it say? Your rule says, the rule for this function of yours says 3 times the input minus 1. 3 times the input minus 1. the inputs. How do we know this is the input? Because the input is the x variable. That's why you can say this rule here says 3 times the input minus 1. Get used to the fact that you read the rule. Read the rule. The rule says 3 times the input minus 1. How do I know this is the input? Because of that indicator. Okay? And so now, what's the consequence? The consequence now say f of h instead of f of x, f of h. That means the x, the input, is now substituted by h. So 3 times the input, but the input is now substituted by h. So 3 times h minus 1. So we consequently, and it's the way it is, and anyone arriving at this video lesson should be fluent enough with substituting an expression into another expression. Okay, so we consequently ended up with something, instead of a number, we ended up with another expression, 3h minus 1. Okay, I brought up for this function. So now, at least for the current time being right now, unless later on when I define otherwise, right now f is that rule, f of x is that rule 3 times x minus 1. Okay, so let's organize our work a little bit. Okay. So as far as the input was regarded, or it was notated as the variable x, as the letter x in our expression here, and we used a few different inputs. We used -1, 1, and 4. Okay, and we even used h, and we even used h plus 1. Okay, the idea I'm about to show you, which is also a very convenient way, and I will formalize all this idea right here, but we can also put all of the results we have done, we can organize all of that into a table. Okay, so the outputs, now we can organize that into a table. So when x was given to be -1, then we calculated our expression to be -4. Okay, when it came to 1 right here, when it was f of 1, when input was 1, okay, then our final output was a +2. Okay, when the input was 4, we came to the output being 11. Okay, and when our input was a little bit abstract here, but h, then we came up with 3h plus 1, and I mean -1. Okay, and when it's h plus 1, we came down to 3h plus 2. Okay, so these are all the outputs. So now the idea now is that any of these different outputs, they switch values. They switch values, don't they? Okay, and now I don't want anyone to be too worried about these expressions. So let's erase out these expressions right here. Let's just focus on the part where we have the numerical values right here. So values, but in the end, all of these commonly share a meaning. These are the different various output values of this particular given function. So that's why very commonly you see a lot of people give the output another variable. It's a y variable. Okay, it's a y variable. So now in that way, what makes sense now is that we can see that the y as your output, any value of the output equals to, see, any value of the y variable, okay, equals to the output of the function. That's why this form right here, or specifically for this case, since our function is known to be a 3x minus 1, y equals 3x minus 1. Ladies and gentlemen, this is called the equation notation. Okay, quite commonly used as well. The equation, I shouldn't say equational, just equation function. I mean an equation notation. Okay, of the function f of x. Okay, it's just, so you have seen the formal, the standard notation. Function's name, input indicator, and then the rule that helps us determine the output. And here, once we agree at this point, once we have seen the idea that the outputs can be a value, right? Then any of these outputs value can be regarded as a variable. So in that case, and whatever we named it, now we have here in this table here I named that y, so y equals y is a variable that equals the output value of this function. And then specifically in this case right here, it's y equals 3x minus 1 right here. Okay, and so for any of you who came out, who enroll into, who are learning this video after you have learned about a linear equation, then that, yes, in this particular problem, that y equals 3x minus 1 is a linear equation. Okay, but now specifically in the concept of a function, then this is the equation notation of our function f of x, whereas this is the standard notation. Okay, this is standard notation. All right, example 1. And so in this example, I am going to give part A, part B, part C, but each part under this example is one separate problem on its own right here. So I would like to give as many as possible so that you can see the flexibility. You can gain some good flexibility, and you can see the universal property of that. So here, part A, I'm going to start out with saying I'm going to be given. I'm departing. I'm using f of x again, but now I'm writing that as 5x minus 4. That means officially in this lesson we are done with f of x equals 3x minus 1. We're done with that. So now I'm taking that name. I'm taking that name to define another function, a different function. Okay, so now starting at this point on, f of x means a different expression. And there will be quite a few occasions out there, quite often in your mathematical life that you will see f of x again. So just every problem has a different definition for f of x. So here in this problem, your function is named f, no longer the other f. Okay, this is a new f. It's this rule right here. A variable x times 5 minus 1. Minus 4. 5x minus 4. And so now this indicator is indicating that this variable is the input. Okay, that means when we're giving a value to substitute for x, then we're going to have to substitute that into this x right here. Okay, so we have a function, there you go. We have a function evaluated, given right here, defined. That's another name, that's another way of saying our function f of x is defined to be 5x minus 1, minus 4. So this is the rule, that's the function. So now 0. Okay, so now it's an indication. It's indicating that I want to come out with the outputs. So f of 2, here's how I'm doing it. The function's name is here. This name means that I have to use this rule. So 5 times the inputs, but now the input is substituted by 2, is given to be 2. All right, so 5 times 2 minus 4. Okay, and it gets me the output. It gets me the output 6. Okay, 5 times 2 is 10 minus 4, that's 6. So this is input, and this is how we use the input. And then now that's the output. Okay, and then the problem required us to also do f of negative 1. See, so this is an indication. And now once we see that indication, we know what to do with that. Negative 1. So the rule says 5 times the inputs, now substituted by negative 1. So 5 times negative 1 minus 4. And that gives me negative 9. Okay, and then f of 0. See, and along with the way I'm saying it out loud so that you can start getting used to it. This is saying f of 2, f of negative 1, f of 0. Okay, and now this is going to be 5 times 0 minus 4. Okay, the output, negative 4. Okay, all right, and so now, again, just like in the earlier problem that I brought up, now it's a formal example. Let's organize this, and I will formalize all that idea. I will re-emphasize all that idea right here, but 2, negative 1, and 0, these are inputs. These are inputs, okay? And then 6, negative 9, negative 4 are the corresponding outputs, okay? So now we can organize them all in a table, okay? Negative 1, 0, 2. We didn't do things in this order, but at least I can decide to put the order of the input values in a certain order. So top down right here means from negative 0 to positive, and then negative 1 correspondingly gave me negative 9, 0 gave me negative 4, and 2 gave me positive 6. Okay, so now yes, this was inputs. Okay, and these are the outputs. We organize them into a table. Okay, let's see. So the variable used here in this problem, that's the variable, the letter is used here is x to represent the inputs variable. Let's put it there. But for the output, like I said, it's just a letter's name right here. We don't always have to go with y. You can call this z. Okay, so the output here can be called z. Okay, so or y, maybe for anyone being a starter, let's just use y to get you comfortable, and then later on, as you are flexible enough, I can start using other letters name. But be aware, this doesn't always have to be y for the output, and the same with x right here, the same with the input. It doesn't always have to be x for the input. Okay, so now in the way how I see, you can have y equals f of x. Okay, that's just nothing unusual, right? Or more specifically, this form right here, you can write it as, and this is not the main aim of the example, it's just the optional extra part that I want to put in to prep anyone for the next step right here. But this is y equals 5x minus 4. Okay, all right, so these are the value that we calculated. This is the end of our example, but additionally, I put in this component right here, and this part right here is the equation notation of our symbol, of our function. All right, so let's get comfortable again. For a function's name, how about let's use a little different letter, g. Okay, g of x. Okay, so how about x squared minus 4x plus 1. Okay, so it's a different rule, and this rule here is regarded as a function with the name g. So g of x, as the rule says, square the input minus 4 times the input and plus 1. Okay, and then the goal of this problem, part B of example 2, let's evaluate g of 0, g of 1, and g of 3. Okay, and so now this indication is indicating that g of 0 means, now there's no reason to use f. Don't use the 5x minus 4 because that was f. This is g. Okay, so we have to take this rule that comes associated with that. So g of 0. So now this indication here is indicating that we're going to substitute 0 for our wherever it's known to be the input. So the input here appears in a few places according to this rule. So it's going to be 0 squared minus 4 times 0 plus 1. We substitute wherever you see the x with 0. Okay, and so now here the rest of the job here is just to do a final calculation. 0 squared is 0, 4 times 0 is 0. These two terms are 0. That's just 1. So this is output. Okay, we're done with one problem, one little problem. That's the end of this particular problem. And then g of 1, another requirement, another request of the problem here. Okay, so 1 squared, because the rule says we square 1 and then minus 4 times 1 plus 1. See, I really love that my student will understand a function is rule. So that's why I keep saying the rule says, the rule says. Okay, and so now 1 squared minus 4 times 1, the input, plus 1. Okay, that gives me minus 2. Okay, 1 squared minus 4 times 1 plus 1. And then g of 3. So now it's going to be the input square, that's the first term, minus 4 times the input. Okay, and then plus 1. All right, and so now it's negative 2 again. Okay, and so now here once again, 1 input comes out with 1 output. 1 input comes out with 1 output. Okay, one input comes out with one output. Someone may be worried about this one output has two inputs. That's okay for a function. Nowhere in the function definition says we cannot go that way, as long as inputting one value, giving out only one value. We're good with that. Okay, and so now that's the end of the example, but optionally I would like to organize all of these input and output in a table. In and out, input and output, that's the X. So this time, as anyone is viewing the video is starting to get a little better in terms of comfortability with the idea of using function notation. So let's now, instead of calling the output the Y variable as the tradition's been using, then let's just call this is Z. How's that? Okay, and so when X, the input variable, equals 0, we had an output 1 recorded here, and that was done through the calculation. That's why I said, the rule determines the output. Okay, when input was 1, okay, the output came out being -2. When input was 3, okay, the output came out being -2 again. Okay, so using a table, it's just a way, it's using the table here in this case, after we have done with the function, it's a way to represent the function. Okay, all right, and so let's try again to get comfortable. And by the way, so with this, since I assign all of the output values as a variable Z, so you can say that in this function we can come up with an optional equation notation right here. Z equals x squared minus 4x plus 1. Yes, it's our function, but instead of written in standard notation, this is equation notation. Okay, all right, so part C of the example. Let's say we're given a function, how about h of x, okay, and that equals square root of x, and finally h of -1. Okay, so 4 little problems indicated here. So h of 0 as indicated, see, it's an indication. The rule says for whatever input that is, the rule says we take square root of that input's value. So now what's the output? Okay, so now it's clearly a mathematical operation. Can we take square root of a 0? Yes, we can. The answer is as an output 0. Okay, so now we have an output for that. It's a successful one. All right, so h of 4. Okay, h of 4. It means now we give this value for the input. We're giving in the value 4 for the input. The input is x in our problem. So now x is substituted by 4. So square root of 4. Simple enough. And hopefully in the later problems I won't have to verbalize it out as much any longer. Okay, so square root of 4, mathematically 2, or numerically 2. All right, the calculation, the understanding with your basic understanding of square roots, you know that the answer, the outcome here, the output here has to be 2. All right, and then h of 1. So h is this rule over here. The rule says we take the square root of every input given. Okay, so now square root of 1. Square root of 1 equals 1. So this is input, that is output. Okay, we're done with another problem. And you can see that I already pick up pace a lot faster compared to part A that I was doing it. Okay, so now how about h of -1? So that gives me a square root of -1. All right, so let's assume that right now we're only working with the real numbers. Let's assume that we're working only in the real numbers. Let's forget about complex number and any of that. That's not what the expectation of this lesson right here. So if we're only restricting ourselves, or if we're only working with the real numbers, then this value right here has an undefined value. We don't know what value that is. We don't know how to find the final outputs for a square root of -1 without learning the imaginary number or complex number. So here, in other words, we don't have a final output defined for this. Okay, it's just the way how our rule, it reached to a limitation. Okay, we don't know how to calculate square root of -1. So in that way, now I'm saying that this here, the answer is undefined. Okay, the answer is undefined, meaning we don't have a final output value for that, because this kind of operation, this kind of work right here, okay, does not take this input. It doesn't know what to do with that input, and we don't know what to do with that either. Okay, all right. So, okay, so for input, we can quickly again organize all of those values: 0, 1, and 4. Okay. And then that gives me a 0 here, a 1 and a 2 here. See, input and output. Now, since the function already called the input variable, any of the input values, a variable x, okay, then here, how about the output? Here we can just call that, and I purposely try to stay away from y. I want you to break away from that that tradition of, y has to be the output and x has to be the input. Nope, it doesn't always have to be like that. So let's call this w, okay, lowercase w. Okay, no one's going to hurt us for that. No one's going to hurt me for that. Okay, so here the equation notation of this function, you can say w equals h of x. X is the input, w is the output. Okay, w is the output. And then so now, in the way how I'm seeing this, okay, so w equals square root of x. W equals square root of x. Okay, all right. Q of x equals 1 over x. So, and let's evaluate q of negative 3. Okay? And so, q of negative 3. The math is straightforward here. And the rule is clearly to understand. The rule says for whatever inputs we're giving in this function, for whatever inputs, we're going to go 1 divided by the value of that input. Okay? So, the rule says 1 divided by the input value. Okay, 1 divided by negative 3. And so now that with our understanding of this kind of operation, then it's going to be the final answer is negative 1/3. That's your output right there. Okay. The question also asks you to evaluate q of 2. We try a negative number, and now we try a positive number. Okay, that gives me 1 over, the rule says 1 over the input value, 1 over 2. Okay, and now that's just simply the 1/2 value. So numerically, or in decimals, this is about a negative 0.33 and a lot longer, and this is about a positive 0.5. Okay, but writing fraction as a decimal is not a requirement. At least in my class, I never require my students to be able to write these in fraction. As a matter of fact, I prefer that my students can leave the answers in fraction and get comfortable with fraction. Okay. And so now, how about q of 0? Just write it down. Just write it down. You don't need to worry anything too far ahead. Okay? Just write it down, q of 0. And what it means, just like how I have done that earlier, what it means is 1 divided by the input being now 0. Okay? And then now let's proceed according to the rule. According to the rule, 1 divided by 0. Oops. We don't know how to divide by 0. Okay? And if now maybe this is the first time that you hear my own joke, but as long as we are human on earth, we will never know how to divide by 0. Mathematicians for generations have tried, but unsuccessful. We've never come up with a way to divide by 0. It's just a mystery on earth. Okay? So now I have to say undefined. We don't have a value for that. Just similar to the earlier situation where square root of negative 1, okay, or in general square root of a negative number, we don't have a value defined. We cannot proceed with the calculation, so we call that we have an undefined value. So the rule is just the rule. And now that I start leading you into that way, and we will get there in some other lesson right there, but there's in the way how your function is, in the way how your rule is, some input is impossible. Some input is impossible to be substituted, to be given into a function. And we will get to that idea more specifically later on. Okay, but for now, just for this rule, according to this rule, the way how it was written, the way how it was defined right here, then it cannot take this input. So input 0 is undefined. Okay, we don't know what the output is. All right. So again, in that way, we're done with part D, surprisingly. And again, let's give that a letter. I mean, let's organize all of the values in a table again. So input, outputs, and now do we always have to put the input on the left column and output on the right column? Nope, doesn't even have to. You can put input here and output there. You can even put your table in a side way where input and where's output right here. The point is you're understanding what you are doing. Okay, and so now I have done -3 and 2, okay, and 0. Okay, and we had undefined here. Okay, we had undefined. This is a negative 1/3 as the output, and this is positive 1/2 as the output. Okay, and so the function already in the problem already named this variable for the input x. So now we can name this. Okay, you can call that whatever letters. I'm running out of creativity on my own. How about let's just call that s. Okay, let's just call that s. So here I'm seeing that s equals to, in this problem at least, s equals q of x. But then specifically s equals 1 over x. Okay, this is the equation notation. This is not the part of the example, but I just decided to go a little extra. Okay, a little bit of an extra mile right there. All right. All right. So now, after I completed the table and before I finished writing down the exact the request of the problem, the final instruction of the problem telling us what to do with this function, then let's try to understand what that function is. So you see, these are the different inputs, and these are the different values of the x variable. But then according to the way how we read and understand about after we have our understanding on the function notation, then the x here is playing in the role of the input. Okay, and so now, just in that way, this function, this table lists down a few different values for our input variable. Okay, and so now we are about to understand what these corresponding values for this f of x row right here. Okay, so now we want to evaluate. Okay, so f of 3. Okay, so this says out loud, this reads out loud f of 3. But it now means, so I want you to be in a completely different situation compared to the earlier example. In example 1, things are easy. We saw the rule clearly as an expression, as a formula. Any of those problems we were doing back in example 1, we saw the rule clearly. Okay, we have seen a rule written down specifically. Here the rule is right here. It's right through this table. It's a surprise, it's maybe a shock to anyone in the first time, but it's time that we start getting used to it. Okay, so here's the rule. The rule may not be explicitly written as a formula as you have seen in example 1, but here's the rule is telling us that, hey, when input equals 3, when the input variable equals 3, this is the output. That's what the meaning of this table is. Okay, so this table is not only representing the function, but it also defines the rule of our function. So I don't need anybody viewing this video to worry about representing the function, but right now this table defines the rule of our function. So the rule says, and is that a 2x minus 1, is that an x squared? That's not the matter. The matter is right here. The rule says when your input is a 3, you're outputting, okay, you come out with an output being 7. Okay, so right there, that's how we're reading it. All right, and so now once we're clear with the idea of how we read output's value right out from a table, and now you are starting to get comfortable, you're starting to be acquainted to the idea of having a function, the rule being given as a table. And it's quite limited, but that's all here. Okay, so now, aside from that particular little evaluation problem. What about f of 5? Okay, so f of 5, input is 5. The input is 5. So now we're going to look it up on this chart right here. When input is 5, where's the output? Right here. And that's why we had that label at the heading of this bottom row over here. The label is f of x, is indicating that the outputs, that's what it's for, the output. Correspondingly, when the input is 5, the output has to be 8. Okay, input, when it comes out to 5, output is 8. Okay, that's how it meets with that entry right here. Okay, and so now output is 8. We found the answer right out from the table. Okay, and so in that way, well, what about f of 2? The way we're saying it out loud, f of 2. Output value, input now is 2. So on the input row, we search out to x equals 2. And then when x equals 2, correspondingly, this table tells us that the outputs, the value of the function has to be 6. All right, so that's the output. Okay, so how about another one? F of 0 equals, okay, so in this case right here, what do I have? F of 0 equals, do we have a 0 here among the inputs? Among the input values being listed in this table, we don't have one. We don't have one listed for x equals 0. So consequently, we don't have one. We don't have a value corresponding for x equals 0. So in this case right here, we have seen that term earlier. This is where, again, I'm saying this other part of the board right here, f of 0 equals, well, it's an equal, but really the answer to that is an undefined. All right, so now we have seen and investigated a few cases. And the idea, and my whole intention, my entire intention of this problem is to introduce, to get anyone learning from this lesson, to get anyone learning from this lesson acquainted to the idea that a function can not only be given as an explicit formula, as you have seen earlier in example 1, but a function can also be given quite commonly as a limited table like this. And any input values that's not listed in the table, we can just simply say that the answer is undefined, because there was no rule for that input. There's no rule for that, what's coming out of that input. And that's what undefined means. Okay? All right, and so now, since we're still wrapping up with that idea about being able to work with the function notation right here, then there are a few other details that I would like to emphasize on. Okay, and so let's look back at example 1, and I'm going to pick maybe 1 or 2 problems from example 1 right here. So I'm going to say back to example 1. Okay, and let's say, how about out of just a random selection right here, I'm going to pick part B right here. So we had our function there given to be, so that was the one we worked with. Part B was, it was a g of x, okay, and the function was x squared minus 4x plus 1. X squared minus 4x plus 1, and we came down to a table of values. So in the problem itself, I clearly indicate which variable was the input and which variable was the output. We got it all clear at the end of that example 1 part B already. And then I still remember clearly I called this, this was z equals x squared minus 4x plus 1. That was in equation notation right there. And so as far as the table of values, see, the x now and the z has one column. It doesn't always have to be input on the left hand side and output on the right hand side. It doesn't always have to be like that. Okay, but so here's the thing. I want to emphasize a few other things before we moved on earlier. See, for this problem in part B, the problem asked us to do x of 0, g of 0, or x equals 0, x equals 1, x equals 3. Okay, and then we came out with final output value, and that was a 1 here, and that was a minus 2 here, and that was another minus 2 for these for the z column. So that was the table of values we've seen back at the the problem itself right there. Okay, so nothing surprised about this. Nothing surprised about this. But so here's the thing. Just simply looking at this. Now I want to enforce another term right here that you might have seen here and there already, but it's now time to formalize it. You see, in this table of values, right, when we're looking at that, and we were clear with the fact that the x here was the input. And so now think of how we have been doing it. So there's no rule that we have to choose the inputs in such a way, that way. So in other words, there's no restriction about picking a value for input. I mean, the problem suggested these values 0, 1, or 3. Once the rule was given, the problem suggested for us that 0, 1, and 3. But I could have also made another table. I could have also chosen for myself the input x and the output z to be, you see, I could have also chosen, completely disregarding these 0, 1, and 3. 4, -1, and -3. I can select these values completely randomly, okay, and independent with whatever suggested from the problem itself, okay. I might have said the textbook, but that's really just my own problem that I prepare right here. But see, here's the thing. So that's the reason why input variable is very commonly regarded as the independent, because we can choose it independently, the independent variable. Because think about how it was done right here. We can independently, I can choose 0, 1, and 3, okay? Anybody else can choose these values and even more values. You can, I mean, to keep the problem short, we went with 3 values to try for substituting in x, but we can keep going further. We can keep throwing in more values. And then no one is telling us that we have to choose 0, 1, or 3. That's what I meant earlier by there's no rule about what values to choose for the x. There's no rule about what to choose for the x. Okay? And that's why it's independent. But now for the y value, now with this function we have a specific rule over here. So the z, now I set the y value. See, once again it shows clearly that I'm still stuck with that tradition, but here I chose z as the output. Okay, so the tradition is a lot of times y is the output, but it's not always. I want students who study with me to be, stepping away from that tradition right there, but z here is the output. So the output is a lot of time very commonly regarded as the dependence, okay, the dependence variable. And now it's a good time to learn about these, because see, a lot of times when you are writing your function in you're writing your function in an equation notation like this, then between the two the variables being present here, then the x here is playing in the role of the independence variable, and the z variable, it's another variable. This is a variable, the other one is a variable, but this variable z here has value depending on what we gave out first in line for x. Okay, that's why the output variable is regarded as the dependent variable, okay. And so just like that, so that's how it happened throughout the entire example 1 right there, the entire example 1, okay. On that example 2, so our function in the end, the table of values we've had was x and then y right here, okay, 1, 2, 3, 4, 5, okay. But see, this y was agreed to be, these values 6, 7, 6, 8 right there, okay. And then we saw at the end of the example 2 that we can write. So this table was the rule for, we take any input here, we choose any input randomly on that given table initially, and then we come out with that value dependently. And so in that way, once again, we came to that conclusion that y, the value for this variable y, because we assign the y variable to these output values right here. So the y variable, okay, is the y variable is the dependent variable, okay, and the x right here, see, the table was given, but you see we can start out doing x equals 5 first, or we can start out being x equals 1 first, and then hit out to x equals 0, which was an undefined case right here. But see, in the end, the inputs there was the independent variable. All right, so now you are familiar with all of those terms that are being used out there throughout math professors and other people doing math and mathematicians. Okay, and so now some more understanding. So now as I'm introducing that idea about, in an equation setting like this, then one variable must be the independent variable, and the other one has to be the dependent variable. Then think about in that setting, then it's, again, if we're looking a little further into this equation notation of any of your function right here, then the dependent variable always stands by itself, coefficient 1, no special power, just one standalone single variable by itself, like a 1z, 1y, that's it, not even a negative, just z equal, okay? And then on the other side, it's an expression, it's a rule, that apply on the input variable, okay? And so now in that way, another way of saying, this is a way to say in words right here, but see, z is a dependent variable and x is the independent variable, and then z equals to the outputs of a function of x. And so in that way, another way of, you will hear people say a lot of times is, in this particular equation, I'm saying that the z variable, I'm talking about now the role of these two variables, how they are related to each other, okay? Then z being z as the function, okay? This equation expresses z as a function of x, okay? See, this equation expresses z as a function of x because z is the dependent variable and x is the independent variable. Or another way of saying, just even shorter than that, right from this equation you can see that z is a function of x, okay? That's another way of saying it, okay? And so now back in example 2 where I had it on the other board right here, then you can see that here this equation says, okay, that equation expresses y as a function of x, okay? Or another way of saying, right from this equation, you can say that y is a function of x. These are equivalent wording. That means the same thing. Okay, it all comes out from the way how we understand about the equation notation of a function right there, of a function.